Make sure. Okay, so this is lecture 12 of 124-105. This will also be the last lecture covered for the test on Tuesday. So just a reminder, you have a test that's opening on Tuesday, and you can sit that until 9 a.m. on Wednesday. So we've been talking about magnetic fields starting from our lecture on Monday. We started by defining what a magnetic field is, and we learned that magnets generate magnetic fields around themselves. And then we went on to learn that moving charges, if you put them in a magnetic field region, they feel a force. And in yesterday's lecture, we learned that because currents are essentially moving charges, currents in a magnetic field feel a force as well. In today's lecture, we will sort of learn that currents themselves, they generate magnetic fields around themselves. So we will we essentially state that currents produce magnetic fields, and from that concept, we will try to determine the magnetic field that's generated by a current carrying wire, and we will use what we call Ampere's law to determine the magnetic field created by currents. And then from there, we'll look at what happens when two wires that carry currents are placed next to each other. So as I said in the very first lecture, there are many parallelisms between electric fields and magnetic fields. So just a quick revision, what produces electric fields again? It's charges, right? So whenever you have a charge, regardless of whether that charge is moving or not, it sets up or it creates an electric field around itself. And for magnetic fields, what produces magnetic fields? Well, we learned magnets produce magnetic fields. But later on, we will actually see that inside the magnets, you have moving charges. So Hans Christian Ørsted, he did an experiment where initially there was a wire and there was no current flowing through the wire. He placed the compass near that wire and nothing happened. But then when he turned on the current and so that current flowed through the wire where the compass was located, he noticed that the compass needle deflected, as you can see in this figure here. And then when he tried to reverse the direction of the current, so that current is now flowing downwards, as you see in this figure here, he noticed that the compass deflected in the opposite direction. Of course, we know now that the compass needle is a magnet itself, right? It's a little magnet, and that's why it can tell us the direction. So if you look at the Earth's magnetic field, so if this is the Earth, the north geographic pole of the Earth actually corresponds to a south magnetic pole, whereas the south geographic pole of the Earth corresponds to a north magnetic pole. Right. And that's why the compass is able to tell direction, because the compass itself is a magnet. The south pole of the compass is attracted to the north magnetic pole of the Earth, and hence it tells us that that's the south geographic pole. Okay, and so Hans Ørsted experiment showed that since the compass needle is a magnet itself, and since it's deflected in the presence of the current, then there must be some magnetic field that exerted a force on the compass needle. And in fact, if you take a compass, like several compasses, and arrange them around a wire, if there is current flowing through the wire, you will see that the compass needles will align themselves according to the magnetic field that's created by the current flowing through the wire. So this is sort of an experimental verification that currents generate magnetic fields. Or in general, let me just erase this. In general, since we've learned that currents are essentially charges that are moving, we can therefore say that electric charges that are moving will generate magnetic fields, i.e. currents. Yeah, they're related. Moving charges create currents. Hence, if moving charges create magnetic fields, currents therefore create magnetic fields. So for the direction of the magnetic field that's created by currents flowing in a wire, we use a right-hand rule. This is, I'd like to use the right-hand grip rule to distinguish this from the right-hand rule that we use for the cross products, right? Because remember, when we were determining the direction of, for example, the force exerted on a moving charge, we also use the right-hand rule to determine the direction of the magnetic force in this case for cross products of two vectors. But the direction of the magnetic field created by the current is also determined by right-hand rule, right? So they're both referred to as right-hand rule, but they're applied differently. So for the direction of the magnetic field, because of a current, the right-hand rule is you grip the wire such that the thumb points in the direction of the current flow, okay, and your fingers curl around the direction of the magnetic field. And hence, that's why I want to call it the right-hand grip rule, because you're sort of gripping the wire in the direction of the magnetic field. And it's the direction of the magnetic field that you get. It's sort of consistent with the experimental observation that around a current carrying wire, the magnetic field forms a circular loop. Okay, so we draw the magnetic field lines as circular loops that are centered around the current carrying wire. Good. As you may have noticed, the magnetic fields, they're circular. And so if you find the direction of the magnetic field at each point along this circular path, notice how the direction of the magnetic field should be tangent to the circular path, but it's changing at every point along the circular path. So just keep that in mind, that the magnetic fields, right, around a wire keeps changing in direction. So for example, here you have a horizontal wire. It carries a current that's flowing to the right. The right-hand grip rule will tell you that the magnetic fields, right, will come out of the page above the wire, and it will enter the page below the wire. Because if you do the right-hand grip rule, right, you point your thumb in the direction of the current flow, and your fingers curl around this straight wire. Okay, so if this is the straight wire here, right? So above the wire, the magnetic field is pointing outwards, but below the wire, the magnetic field is pointing inwards. And so you have these two different directions for the magnetic field created by this current that's flowing to the right. Okay. Good. Right, so that's how you find the direction of the magnetic field. Now for finding the magnitudes of the magnetic field, so how much magnetic field is created by this current in the wire, we use what we call Ampere's law that's represented by this equation here. It's a general, the Ampere's law is a general relationship that relates the current in the wire to the magnetic field that's created by the wire. And yeah, if you search your memory in our past for our past lectures, you will see that this integral equation is very similar to Gauss's law that we learned to find the electric fields Q enclosed over epsilon naught, right? So if you recall our previous lectures, like in the beginning of the course, where we learned about electric fields being generated by charges, we encountered Gauss's law, which allowed us to determine the electric field that's created by a charge that is symmetrically distributed. So the equations look very similar. So finding the magnetic field also uses the similar strategies that we learned for finding the electric field of a charge. So just a few notes about Ampere's law. So in Ampere's law, this is a line integral. The integral here is a line integral, meaning it's one-dimensional. One-dimensional, whereas in Gauss's law, this is two-dimensional because you're taking the integral of an area. Whereas for Ampere's law, you're just taking the integral of a length. A length is one-dimensional. Right? This circle in this integration line tells us that you do the integration along a closed path. Okay? And so what you do is you draw a closed path or a loop, which we call the Amperian loop, and then you do the integration over this closed path or Amperian loop. Okay. We'll look at an example later on to illustrate what we mean by closed path and integral of a closed path. Okay. dl in this integral here is a small or a tiny length vector that represents the closed path. Okay. And then I enclosed, this is the current that is inside the closed path that you've drawn. And we note that since in this equation, you're only looking at the current inside the closed path, it means that only the current inside the path contributes to the magnetic field, as indicated here. And mu naught is just a constant, which is given as this number here. Right, so to evaluate the integral and evaluate Ampere's law, right, we have to find a useful symmetry. We have to enclose the current using a symmetric path because then that allows us to evaluate the left-hand side of Ampere's law easily. The symmetric path that we choose will be the integration path that we will do in evaluating this integral over a closed loop. And yeah, usually I think in almost all these scenarios, we will consider the symmetric closed path we will use will be a circular path. Okay, that encloses the current, because usually currents flow through a wire and the wire is cylindrical. We know that the magnetic field forms circles around the wire, and that's why the symmetry that encloses the currents in the wire is a circular path. Okay, so we will usually do a circular path to integrate that, to evaluate this integral here. Because if you choose the correct symmetry, right, this integral just becomes either B times L if the magnetic field is parallel to the integration path, or it's equal to 0 if the magnetic field is perpendicular to the integration path. So by choosing the correct symmetry, this integral here reduces to either B times L or 0, depending on the direction of the magnetic field in relation to the integration path you chose. Right, so that's essentially, we can bump this up into one step. the first step is to choose the integration path. And then the second step is to determine how much current is inside the closed path that you've chosen. And then once you've determined the currents and you have reduced the integral into B times L, it's just a matter of rearranging the equation to find B. Right, it probably will become clearer if we look at an example. So here's an example of applying Ampere's law. Integral of B dot dl is equal to mu naught times I enclosed. We want to find the magnetic fields of a straight current carrying wire, meaning you have a straight wire, there's current flowing through that wire. We want to find, it's actually showing, we want to find the magnetic fields generated by this current. And yeah, by using Ampere's law, we should find that the magnetic field is given by this equation here. Right, so first step is to determine the useful symmetry so that you can determine the integration path that you will use, right? If this is the wire, okay, this vertical line here represents the wire, it's carrying a current, the current is moving upwards. Well, we know from right-hand grip rule, if you have the wire current moving upwards, the magnetic field will form circles around your wire, your straight wire. So essentially, you have circular magnetic field lines around the wire. So it is straightforward that the useful symmetry to use will be circular. So it then follows the shape of the magnetic field around the wire. Okay, so the circle drawn here, this is the circular path, which we will use as the integration path around the wire. Okay. The path has an arbitrary radius r. Right, we then evaluate the integral because we've chosen our closed path. It's a circular closed path. We then evaluate the integral of B dot dl. So we know that the magnetic fields, right? The magnetic fields will form circles around the wire. And notice how the magnetic fields at each point will be parallel to the circular path that we've chosen. Okay. And so because, yeah, this is a dot product that becomes BDL cosine theta, right? But looking at the direction of the magnetic field around the wire, it's always parallel to the integration path, the circular path that we've chosen. Since it's always parallel, cosine theta, well, theta is equal to 0 and cosine theta is equal to 1. Hence, you're just evaluating integral of BDL. And B is constant, you take it out of the integral. Hence, you're just evaluating integral of DL, which is equal to L. So this illustrates that by choosing the correct symmetry around that mimics the direction of the magnetic field, this integral just reduces to B times L. Okay. The question now is, what is L? L is the length of the integration path. It's circular. Hence, the length is equal to the circumference of the circular path, right? R is the radius of your circular path. Okay. Okay. So the left-hand side of Ampere's law, the integral part, then reduces to B times 2 pi r. 2 pi r comes from the circumference of the circular path, which is the length of the circular path. Okay. Once you've evaluated the left-hand side of Ampere's law, the next step is to determine the current that is inside your integration path, right? Your integration path is this closed loop. If you look here, there is the whole current flowing inside your closed loop, right? So the current enclosed, or the current inside the closed loop, is equal to the whole current I, right? And hence just equate now the left-hand side of Ampere's law to the right-hand side of Ampere's law. Okay. Left-hand side is the integral part. You evaluated that as B times 2 pi r. And the right-hand side is mu naught times the current inside the integration path, which is determined to be I. So you have mu naught I. So it's just now a matter of rearranging to find that the magnetic field is equal to mu naught times I divided by 2 pi r. Right. So R is variable. It depends on where you want to find the magnetic field, right? So if you want to find the magnetic field at this point, where, for example, R is equal to 2 meters, then you just change the value of R. So R is the distance, radial distance from the wire to the point where you want to evaluate the magnetic field. Any questions about Ampere's law, how to apply that equation? It's usually, it's a recipe, and usually the integration path is circular. So more often than not, the left-hand side will always be B times 2 pi r. And your main task, therefore, is to find how much current is inside the closed path. Okay. Right, let's try this exercise to see, to apply, for practice in applying Ampere's law. So you have a coaxial cable. The coaxial cable is shown here. It's coaxial because there are two conductors where current will flow, where you have here the main copper wire that's carrying a current, and then you have a copper mesh that carries a return current. So notice how the currents are flowing in opposite directions in the copper wire and the copper mesh. Okay. And then you have some insulation between the copper wire and the copper mesh, of course, to prevent shorting of the circuit of the currents there. And then you have an outer insulation that insulates the whole wire. It's the outside covering of the cable in essence. And we want to find the magnetic field in the insulation here between the copper wire and the copper mesh, and the magnetic field outside the coaxial cable. So any point outside the coaxial cable. Okay, so here is a cross-sectional view of the coaxial cable, which will probably make it easier for us to evaluate Ampere's law and determine, the current enclosed as well as the closed integration path. Again, you have there the copper wire that's carrying a current I. In this particular illustration, the current is flowing into the plane or into the page. Hence, you have this X, right? So the X indicates that the current is flowing into the plane. You have the insulation that's protecting the copper wire from the current in the copper mesh. The copper mesh carries the same amount of current, but in the opposite direction. So the dot here, the yellow dot, tells you that the direction of the current is going out of the plane, right? Okay, hence currents with equal magnitude but opposite directions. And then you have this outside insulation, the outer covering of the wire. Okay, so let's do first the magnetic field in the insulating sleeve. So it's this part here. Right, as we saw earlier, the first step is to evaluate, right, the left-hand side of Ampere's law. You want to find the magnetic field in the insulation here. So that means that you draw your closed loop, right, at any point within the insulation, right? It can be any radius. So let's define that radius R. It can be any radius as long as it's inside this insulation region, because that's where you want to find the magnetic field. Okay, we know that the magnetic field created by currents in the wire, they form circles around the wire, and hence the integration path we choose will be the circular path drawn in the insulation sleeve. Right. The integral then reduces to B times L, because if this is the DL, the small length in your integration path, it is parallel to the magnetic field, the magnetic fields created by the currents in the copper wire, right? So B dot DL is equal to BL, where L is the length of the integration path that you drew. Your integration path is a circle, so the length is the circumference of the circular path, 2 pi r. R is the radius, the arbitrary radius of that circular path. Good, right? Okay, so the left-hand side of Ampere's law is P times 2 pi r. Right, for the right-hand side, determine what is the current inside your integration path. You have the current I inside your integration path, so I enclosed is I, right? Left-hand side is equal to right-hand side, B times 2 pi r, which you determine here, is equal to mu naught times I. Rearranging that, it's mu naught I over 2 pi r. Okay. And if you check your answer, it should make sense, because it's as if you just have a single straight wire that carries a current I that's generating the magnetic field in this region here. Okay. And therefore, the magnetic field is the same as the magnetic field of a straight wire. Good. We're happy with that solution. Yeah. Now, next, what is the magnetic field outside of the coaxial cable? So outside, we're looking at this region here. So that means if you were to evaluate your integral, the left-hand side of Ampere's law, you need to draw your integration point outside the coaxial cable, because that's where you want to find the magnetic field, right? So your integration path is a circle with arbitrary radius r, but that circle should be outside the coaxial cable, meaning radius r of that circle should be bigger than the radius of the outside insulation. Again, because of the choice of symmetry here, integral of B dot dl reduces to B times L. L is the length of your integration path. Your integration path is a circle. The length is the circumference, 2 pi times the radius r. Okay. So left-hand side becomes B times 2 pi r as before. Okay, how about the right-hand side? What's the current inside or enclosed by your integration path? Right? Inside your integration path, you have these two currents, that current and that current. Right? Yeah, the currents are equal, but note how the currents are in opposite directions. Okay, so you have a current that's going into the page or into the plane and out of the plane. So essentially, these currents in opposite directions, they cancel each other out. So overall, the net current inside your integration path is 0. Right? So the current inside the integration path, meaning the current outside the coaxial cable is 0. So naturally, the right-hand side of Ampere's law is 0, which tells us that the magnetic field outside the coaxial cable is 0. And that's exactly why coaxial cables exist, because of these, the existence of these two currents that are flowing in opposite directions. It sort of shields the wire. It shields the surrounding equipment from the magnetic field that's created by the current flowing inside the coaxial cable. Right? So if you have sensitive equipment, usually coaxial cables are used so that the magnetic field generated by the wire flowing in the cable will not affect the sensitive equipment surrounding the wires. Yeah.
For the yellow current, are you able to push through a different element of the center to get a slightly different current?
Yeah, so this one, if you have, yes, it's possible to have a slightly different current in the mesh. In that case, the current outside will not be 0 anymore. Hence, the magnetic field outside the coaxial cable will not be 0 anymore. In that case, yes, it is possible. Yeah. Good. So in general, we have derived that if you have a long straight wire and it carries some current I, the magnetic field generated by that wire is given by this equation here. So if you have a long straight wire, you can just go straight ahead and use this equation to determine the magnetic field created by that current. Of course, substituting how much current is there and substituting the distance from the wire to the point where you want to measure the magnetic field, right? So that gives R. R is the distance from the wire to where you want to measure the magnetic field. Mu naught is, of course, just a constant number, as well as pi. Right, so let's look at this example here. You have two wires. Okay. One wire is carrying a current of 5I in the direction shown, downwards. And then the other wire is carrying a current I, which is flowing upwards, opposite the direction of the 5I current. We want to find the magnitudes and direction of the magnetic fields at point P. A point P is halfway between the two wires, meaning if the two wires are separated at distance 2D, so this distance here will be D for each of the wires from point P. Right, so how do we find the net or the total magnetic field at point P? And just a reminder, for a long straight wire, the magnetic field we derive from Ampere's law is mu naught I over 2 pi r. Okay, the approach here is to find the magnetic field due to each wire and then add them up considering directions. Okay? Do vector addition considering the directions of the magnetic field in order to get the total magnetic field. Okay, let's look at the directions first. So for the 5I current, 5I is pointing, 5I is flowing downwards. So you point your thumb downwards and your fingers curl around the wire to give you the direction of the magnetic field. So that means on the left side of the 5I current, the magnetic fields are pointing into the page, right? And on the right-hand side of the wire, the magnetic fields are pointing outside the page. Yeah, so your currents go around the wire in circular loops. Okay, for the I current that's flowing upwards, if you do right-hand rule there, so on the right side of the current I, you have magnetic fields pointing into the page, and on the left side, you have magnetic fields pointing out of the page. Okay. So of course, at the position of point P, you have magnetic fields going out of the page because of the 5I current, and you also have a magnetic field going out of the page because of the current I. These magnetic fields, of course, permeate through space. Right. So that's for the directions there. For the magnitudes, simply use the equation for the magnetic field of a current carrying wire. Yeah, so you have mu naught over 2 pi. The current is 5I for the wire on the left. And R is the distance between the wire that's carrying the current and the point where you want to measure the magnetic field. So R is D in this case, okay? And you have the direction that was determined from right-hand rule. Similarly, for the I current, the magnetic field is mu naught divided by 2 pi, right? And then the current I is just I. And the distance R is D. The direction is also out of the page as you determined from right-hand rule. So you have these two currents generated by the two wires. They are in the same direction. Therefore, the total magnetic field is just adding up these individual magnetic fields here. Hence, you have mu naught 6I over 2 pi d. And the direction is out of the page, the same direction as the individual magnetic fields. Yeah.
The 5I.
Sorry. If the 5I. This one, yeah. So this one, yeah, they will add up. The 5I and I will add up into 6I. The mu, it's constant. It's there for both. So it's sort of, so if you write this down as net magnetic field, you sort of have mu naught over 2 pi 5I over d plus mu naught over 2 pi I over d. Okay, so mu naught I, 2 pi, and d, they are common in those two terms. So you can factor them out. So you can have, yeah, mu naught over 2 pi I over d, and you're just doing 5 plus 1. Yeah. Good. Right. Okay, so we learned if you have a wire, we can find the magnetic fields using this equation, which came from Ampere's law. The direction of the magnetic field you get from right-hand rule. If we combine that with the concept we learned yesterday, where if you have a current, I mean, if you have a magnetic field and if you put another wire that's carrying a current beside the other wire, the magnetic field set up by the first current carrying wire will exert a force on the second wire, which tells us that, because current will create a magnetic field around itself, if you put a second wire, that second wire will feel the force due to the first wire. In other words, two or more current carrying wires will exert a force on each other. And in general, if the currents in the wires are flowing in the same direction, right, as shown in figure A, the forces are attractive, okay? Meaning two wires that carry currents flowing in the same direction will attract each other. Okay? Whereas two wires that are carrying currents in opposite directions will repel each other. Okay? And if you compare that to the behavior of two magnets, it's opposite, right? So don't be confused about that. We learned that with magnets, opposite poles attract each other, right? So north will attract south, whereas like poles will repel each other. North will repel north. Okay. So for magnets, same poles repel, opposite poles attract. But for currents, same directions will attract, whereas opposite directions will repel. So they're reverse of each other. But magnets and currents, they generate magnetic fields around themselves, and it's through these magnetic fields that currents can exert a force on another current. And it's also through that magnetic field that a magnet can exert a force on another magnet. All right, so for direction of the force, use these concepts here to find the direction of the force exerted by one wire on another. Okay. For the magnitude of the force, right, these equations will give you the magnitudes of the force felt by one wire because of the presence of another current carrying wire. Just some notes on the subscripts here. So F1, the subscript 1 here, F1 here means that it's the force that is felt by current 1 because of the presence of current 2. Right? So F1 here, it's the force exerted on wire 1 because of the current in wire 2. In other words, you can think of this equation as current in wire 2 exerts a force on wire 1. Or alternatively, right, current in wire 1 exerts a force on wire 2. Right? Just the key concepts I want you to remember here is that two wires that are carrying currents, if you put them together, they will exert force on each other. To find the direction of the forces exerted on each other, you use this concept, which, yeah, you can derive this from right-hand rules, F equals IL cross B. And to find the magnitude of the force that the wire feels, use these equations here. For the force felt by wire 1 because of the current in wire 2, it's this equation. For the force felt by wire 2 because of the current in wire 1, it's this equation here. Okay. Right, we can also take a wire, right? If you have a long wire, you can take that wire and coil it into many loops, right? So that you have tightly coiled loops as shown in this figure here, in which case we now form what we call a solenoid. So a solenoid is essentially just loops of wire that are coiled very close to each other so that there is no space between them. Well, there's negligible space between them, so that the magnetic field is confined inside that solenoid. So yeah, as you can see here, the magnetic field is mostly confined inside the solenoid. To find the direction of the magnetic field created by a solenoid, you grip the solenoid in the direction of the current flow. So it's also the right-hand grip rule, except that your fingers will grip the solenoid. So say the current flows in this direction. So you sort of have to determine in which direction the wires are coiled, and then where does the current enter the solenoid. So in that case, for example, you grip the solenoid in the direction of the current and your thumb points in the direction of the magnetic field. So in this figure here, the magnetic field, the current is going out of the page on the top part of the solenoid, and the current is going into the page at the bottom part of the solenoid. So you're gripping the solenoid in this manner, and your thumb points in the direction of the magnetic field. One thing you can notice with solenoids is that the magnetic field is confined in the middle, but it also sort of goes out one end of the solenoid and enters the other end of the solenoid. So it sort of looks like a small a magnet, where you have the North Pole and the South Pole, right? We define that magnetic field lines go out of the North Pole and they enter the South Pole of the solenoid. Okay, so that's how you find the direction of the magnetic field. For the magnitude of the magnetic field created by the current in the solenoid, we use this equation, which can be derived using Ampere's law, right? We will not derive this equation from Ampere's law, but I will refer you to the textbook if you're interested in checking the derivation of this equation using Ampere's law. Okay, N is the number of loops in your solenoid, and L is the length of the solenoid. So it's not the length of the wire, but rather it's the length of the solenoid here. The length of the wire that you use to coil, of course, will be longer than the length of the solenoid, but what we are interested in this equation is the length of the solenoid rather than the length of the wire. And you can also take the solenoid and you can bend it around so that you form like a toroid shape, as shown here. So in that case, the magnetic field created by this toroid will take the same form, similar form as that of a solenoid. So it's mu naught Ni over 2 pi r, right? If you compare that for the solenoid, it's mu naught Ni over L, where L is the length of the solenoid. For a toroid, it's mu naught Ni over 2 pi r. It's because you have a solenoid of length L and you sort of just bend it around so that it forms, you have a circular solenoid, in other words. But we call that a toroid, not a circular solenoid. And hence the length is 2 pi r. R, of course, will be the radius, radius of the toroid. Right, so again, if you're interested in the derivation of this, I'll refer you, it's from Ampere's law, because you have good circular symmetry, and Ampere's law is applicable, well, it's good to use when you have good symmetry. But in some cases, we cannot find a useful symmetry to calculate the magnetic field. If there's no useful symmetry, we use what we call the Biot-Savart law. Okay? Biot-Savart law is evaluating this integral, and the whole idea is if you have this shape, for example, a circular loop here, you can divide that circular loop into small lengths, and you evaluate the magnetic fields of those small individual lengths, add them all up. Hence, you have this integral here, and find the total magnetic field created by the currents in this circular loop, for example. Okay, so in this course, all you have to know is Biot-Savart law is useful when there is no symmetry, no great symmetry, and it's evaluating this integral. But we will not go into the details of evaluating the integral. In other words, you're not expected to evaluate the integral in Biot-Savart law. Rather, it's sufficient to know that for systems without great symmetry, Biot-Savart law is the more appropriate law rather than Ampere's law. Good. Right, so any questions about the topic? So what we've covered is that we learned that if you have a current, that current will generate a magnetic field around itself, much like moving charges will generate a magnetic field around themselves. And we used Ampere's law to find the magnetic field generated by a long, straight, current-carrying wire. Okay, and we can use Ampere's law because of the circular symmetry of the magnetic field around that wire. We can take a wire and wind it into several coils to form a solenoid, and the magnetic field of a solenoid is given here. And if you have two wires that are placed close together, then the current in each wire will create a magnetic field, and that magnetic field exerts a force on each of the wires. Good. All right, so if there are no questions, we'll end our lecture. There's the workshop this afternoon, and I'll see you in the workshop.